do you remember what K5 is? What is K5? It's the maximally connected graph of 5 points, right? So you have 5 vertices, and you think about all possible ways to connect. So every vertex is connected to each other. Okay? So you have that's K5. Okay. Now these only cross each other. There aren't any vertices here, so there are only 5 vertices here. Yeah, so last time I explained that any graph that contains K5 or K33 is not planar. So this is an example of a non-planar graph. No matter how you try, you can't put this in a way that you have 5 vertices and all the edges are not crossing each other. You inevitably have to draw the edges to cross each other. Okay, so that's K5. Now, is this Eulerian? Eulerian meaning that it doesn't have an Eulerian circuit. So can you start from one point and use every edge to come back? What do you think? No. Well, what determines Eulerian?
R.
Huh?
R, isn't it? It's even?
Degrees are even. So all the degrees of at each point, what is it? 1, 2, 3, 4, right? So all the degrees here are 4.
Oh, that's good.
So it is Eulerian, right? So it is Eulerian. Is it Hamiltonian? Well, that's even easier. You start from here, go around, come back, done. It's Hamiltonian, obviously, right? Good? All right. Okay, let's ask a second question. Is K23 Eulerian? Hamiltonian? Okay, what is K23? It's like you have 2 things here.
3.
You have 3 things here. And it's what's known as the bipartite graph. Bipartite graph means that there are 2 groups where inside each group there shouldn't be any connections, okay? But you're only allowed to have connections within different groups, okay? So this point cannot be connected to this, but this is allowed to connect to other ones, okay? And when you have K something, that means the maximally connected graph. So this one, the maximally connected one should connect to every one of these, and this one should also connect like that. Okay. So I didn't have to draw it like this, but I tried to draw it as a planar graph. Okay, so K23 is in fact planar because K23 doesn't contain K33. Right? Yeah. So this is planar. Question, is this Eulerian? Let's count the degrees. This is 2. How about this? That's 2. That's 2. How about this? That's 3 and that's 3, right? Yeah. So it has an Eulerian path that starts from here and ends there, but it doesn't have an Eulerian circuit. So because of these, it's not Eulerian. Okay? No, it has points of odd degrees. Okay? Nodes with odd degrees are present. Is this Hamiltonian? Oh, by the way, the answer to this is yes and yes. Is this Hamiltonian? Yes, that's harder to think. Yeah, is there a path that you start from one side and come back? visit every, start from one place,
Like
visit
this.
every vertex and come back.
I think if you start from the top one,
Top one, can you do that?
I think so. Go up.
No.
Why not?
Well, I drew it differently and I think it works out good.
The answer is no, so you probably drew it wrong.
But isn't it just when you can hit all the nodes and
Yeah, but you're not allowed to
oh wait, I
pass through
forget
the nodes twice.
you have to return back.
And you have to return to the same place. Yeah. Oh, so are you saying that it has a Hamiltonian path but not a cycle?
Yeah.
Where do you start? Here?
Well, I did it different. I did 3 down the middle, then 2 on, and then 1 on the left, 1 on the right.
Yeah, well, let's see. No, I don't even see a Hamiltonian path here. But I feel like yeah, so the way you figure this out is if you had a Hamiltonian path and only drew the path itself and ignore the other edges. So think about this. If you have one, just like that, right? Then if you have 4 of them, and five of them. So if I just draw the Hamiltonian path from here, it's just this, right? That's a Hamiltonian path, or a Hamiltonian circuit, okay? So if you have a Hamiltonian circuit, then what you end up with is like you only have 2 connected graphs, right? Because you go in and then come out, right? So such graph is 2 connected. Uh, so how do I argue this? About what the argument was. Goes once. Okay, right. Okay, so the argument goes like this. Right, so it's not about the 2 connected. That's an observation that you can make, but here's another one. Uh, because this is a bipartite graph, every time you take an edge, you're in the other group, okay? So if I say this is the blue group and the other group is the red group, right? Then if you take any path, then it's always from red, blue, red, blue, red. You see that? Okay, yeah. Oh, okay, so if you start from here, you have a Hamiltonian path, which is you start from here, come back here, do that, go here, and there. That's a Hamiltonian path, right? Yeah. But if you have red, blue, red, blue, red, right? You visited all the 5 points, but the beginning and end will be different, right? Yeah. And there's no way to start from blue and end at red because it'll be blue, red, red. So you end up with four points you visited, and the 5th point you can't visit because It has to be one of the blues, but it has to be one of these 2 points. Okay. So if you start from the blue group, there's no way to have a Hamiltonian path. If you start from the red group, you always have a Hamiltonian path that begins and ends at different places. Yeah? But then there's no way to make this last one to be the same as the beginning one. Okay. So that's the argument you can make to show that this is not Hamiltonian. Okay? So the answer is no. Okay. Now there's a if you ever learned any graph theory, there's a famous graph that everyone should know. Learned graph theory should know one. So you start with the star in the middle, okay? And then you connect it like that, and connect outside. So it's like K5, but these lines are deleted, and then you have an external things right here. Okay, so that if you count the edges, these are not vertices. Okay, so if you count the edges, there will be 15 edges, and there are 1, 2, 3, 4, 5 vertices in the middle, and then 5 outer ones. So there are a total of 10 vertices. So this was known as the Peterson graph. It's an important graph because so many examples in graph theory uses this as a counterexample to various conjectures you can make. And this one is not Eulerian because these degrees are 3, so not Eulerian. But then if you try to do Hamiltonian, it's a bit hard to show that it's not Hamiltonian. It turns out that it's not Hamiltonian. But it does have a Hamiltonian path because in here you can go right to visit all the interior ones, and then from here you can visit all the outside ones, right? But then if you look at where this lands, we start from here, I think. Yeah. So you can't, there's no route from here to there. If there was, then it would be Hamiltonian. If there was a connection from here to there, it would be. Yeah. So you can try to make a Hamiltonian path, but you can't find a Hamiltonian circuit. Okay, that's called the Peterson graph.